So last week we have discussed the 4 versions of proposition 7.5.1. Okay, and so we will generalize this proposition. Okay, so let me see. Proposition 7.5.1. Okay, can be generalized as stated all right in the following proposition. Okay, and I will give a title for this proposition. It is called the existence and uniqueness of conditional expectation. Okay, so let X be a non-negative random variable or a random variable with finite expectation. And y1, y2, up to yn, arbitrary random variables. Okay, so the random variable, if it is non-negative, that's fine. But if it is not non-negative, then we require that this random variable has a finite expectation. Okay. And the sign information, y1, y2, and yn, can be arbitrary. Okay. Right now, there exists, okay, so this is the existence, a Borel measurable function G from the n-dimensional Euclidean space to the real line such that the expectation of X can be computed as the expectation of G of X, Y1, Y2 up to Yn. Okay? All right, so the existence tells us that there exists a Borel data processing function G, okay, which on Rm, which means that this function has n variables. And so we use G to process the sign information. We have n sign information, y1, y2 up to yn. Okay? Right? So we are able to do the data processing on the sign information. And the expectation of this result gives us the expectation of X. Okay, and in proposition 7.5.1, we actually establish such a data processing function, but restricted us to only consider only one sign information. Okay, in that case, because we explicitly establish such a data processing function, right? So actually, in 4 cases, we accepted that. But this is generally true, okay? Not necessarily only one of the 4 cases. So you can be other cases. Okay. The only requirement is that either x is a non-negative random variable or a random variable with finite expectation. Okay. All right. So we have the existence. How about the uniqueness? Okay. If there is another Borel measurable function G prime from the n-dimensional Euclidean space to the real line and satisfying okay, so this is, we say here 7.5.1 point A, all right. Then the data processing on the unsigned information by G and by G prime will be equal with probability 1. So this is the second part is the uniqueness, but the uniqueness is in terms of with probability 1. Okay, so these 2 random variables will be equal with probability 1. Okay, so they have the same statistical properties. So the random variable G of y1, y2 up to yn is called a version, okay, of the conditional expectation of x given y1, y2 up to yn. So that's, we may rewrite (7.5.a) as here. The expectation of x is equal to the expectation of the conditional expectation of x given y1 up to yn. Okay. Okay. And because these 2 random variables are equal with probability 1, so if you use G to replace as the version of this conditional expectation, or you use G prime, they will give you the same result. Because these 2 random variables are equal with probability 1, and as we have discussed before, they will have the same nth moment. Okay? In particular, they will have the same expectation. Okay. All right. Okay. And now we next So we next list 3 important properties of conditional expectation. First, proposition 75.b called moving out property. Right? So let X be a non-negative random variable or a random variable with finite expectation. And y1, y2 up to yn, arbitrary random variables. Okay. And let z equal to, so z is a data processed result of the sign information y1 up to yn by a Borel measurable function h. So for some Borel measurable real valued function h okay, so that z is non-negative if x is non-negative, or z times x has a finite expectation if x has a finite expectation. Right? So z is a function of the sign information. Okay? Z is sign information. Then the conditional expectation of the product given the sign information y1 up to yn, okay, will be equal to z. So you can move z out of the conditional expectation sign. It's z times the expectation of x given the sign information with probability 1. Okay. The intuitive reason is that once you know the sign information, then you should know z exactly, because z is a function of the sign information. Okay, so that z has been determined, right, by y1, y2, and yn. So you can move it out, so you can regard it z as a constant. Okay, so you can move z out of the conditional expectation sign. Right? So I give you a title called moving out. a very intuitive title to have. Okay, so this is the first property we call the moving out property. The second property is called the independence property. Point C. Alright, so let X be a non-negative random variable or a random variable with finite expectation. And y1, y2 up to yn arbitrary random variables. Okay? Now, if X and the collection of sign informations, okay, are statistically independent, then, okay, so the sign informations may depend on each other, right? So this collection may depend on each other, but the whole collection is independent of the X, okay? Under this condition, then the conditional expectation of X given y1 up to yn will be equal to the unconditional expectation with probability 1. So it is become to a constant. Okay. And the third property we have proposition 7.5.d, we call the refinement property. Again, let X be a non-negative random variable or a random variable with finite expectation. And y1, y2 up to yn, arbitrary random variables. Okay. Oh, we have extra. y1, y2, yn, and z1, z2 up to zk. So we have n plus k sign informations, arbitrary random variables. Then the conditional expectation of X given the sign information y2 up to yn will be equal to that you can give at first more sign informations So except the Y sign information will add the Z sign information there. Okay? Which means that you are given more information. So it becomes more easier to find this conditional expectation. Oops, I'm sorry. Okay, so you can first find more sign informations and compute this conditional expectation. Then you will compute the conditional expectation. Okay? With probability 1. Again. So in 2 steps. So this is a very good identity. All right? Because once you are given more sign informations, the computation of this one is much more easier to deduce. And once you do that, then you condition the original sign information again. Okay? So this is called a refinement. You can refine the sign information. Okay, you give more. Okay? But if you do it in the other way, so if you if you do that, you consider the sign information, the refinement later on, then actually there is no effect. Okay. The reason is that once you have this one, this is a function of y1, y2, of yn. Okay? And as a function of y1, y2, y1, so that it's a function of y1, y2, y1 up and z1, z2 up zk. Okay? So that because this information is finer than only this information, so this is, if this is given, then this random variable can be regarded as a constant. So you can move it out by moving out property there. Okay, so you can move it out, and this becomes 1. All right, so that the expectation of a constant, the conditional expectation of a constant given sign function will be a constant again. Okay. So the second identity is from the moving out property. Okay. And so the new thing is the first equality. Okay. So the first equality is quite useful to find them. Okay. So you can see here, to compute the expectation of a random variable, if it is not easy, then you can do it in 2 steps. First of all, right, you can use a sign information y. But if the computation of this one is still not easy, then you can do it. right? You can give one more sign information. All right? Once you've done that, then you compute that with little sign information. And then you do it. So you can compute it in 3 steps, right? By the refinement property. All right? So you first compute given y and z, all right? And then you compute the continuous expectation of this random variable given y. And then you take the expectation. Okay? Or if you think about that it's not easy again, all right? So you can y z w, okay? And then y z, and then y, and then again. All right, so you can refine the information more and more, right? By applying the refinement property iteratively. Okay, so to compute the expectation of x, if you do that, you will do that instead of 1 step, you do it in 4 steps. Okay, in 4 steps. Okay, first of all, you use 3 sign information, okay, and then use 2 sign information, and then 1 sign information, etc. All right, so there are many different ways, right? You can. This is just one possibility, right? There are other many possibilities to do it. Okay, depends on, so a proper chosen sign information will facilitate your computation. Okay, so your job is to find out what kind of sign information would be more useful than the others. Okay, with others, right? So this depends on your judgment, depends on your understanding of the problem you deal with, right? So this all this property, these 3 properties are very important. The independence properties is very useful, as you can see. It's truly simplified your, okay, that. So for example, if x and y are not independent, if not, but it is possible if the case that x is independent of the collection of y, z, w. It is possible, right? Maybe it is possible. Okay. Then you are lucky if this is the case. Okay, but so there are a lot of choices for you to take. Okay. So any questions about these 3 properties? Okay. So you have to understand the statement and then use them. Okay. Because at this moment, their proofs would be unreachable for you right now because we do not prepare well to prove that. Okay, but they are. But you know that I will give you a couple of exercises to prove these properties in special cases. For example, for discrete case, okay, for discrete case is quite easy to prove them. Okay, for discrete case. For jointly absolutely continuous cases, you may be able to do that. Okay, but they are very general. Okay, they are very general. Any questions? Okay, now an application An application is to use conditioning to compute the probability of an event. Okay? Right. Now, so let's 1 sub A be the indicator. Function of an event A in the sigma algebra F. All right, and y1, y2 up to yn, arbitrary random variables. Now, an indicator function always non-negative. Okay, always non-negative. So propositions 7.5.a, b, c, d can be applied. Okay, can be applied. So with the conditional, expectation, E1 sub A of the indicator function 1 sub A given y1, y2 up to yn we have here the expectation of the conditional expectation of the indicator function given the sign information, okay, is equal to the expectation of the indicator of the event A, okay, by proposition 75.8, okay. And this is actually the probability of the event A. Okay? So expectation of the indicator of an event is just equal to the probability of event A. We have that. Okay, so that's this condition expectation is also called the conditional probability of event A given the sign information y1, y2 up to yn, and denoted as P of A given y1, i.e. the probability of A it's actually the conditional expectation, okay, the conditional expectation of the indicator of event A, and then we know the PA is actually equal to the expectation of the conditional probability of A given y1, y2 up to yn here. So this is a random variable. So this is actually a function, Borel measurable function of y1, y2, up to yn, so that it is a random variable. So conditional probability of an event A given some information y1 up to yn, this one is a random variable. Okay? So it's a random variable. And you can take the expectation of this random value to get the probability of A. Okay. All right. Now, I'll give a couple of remarks. When y is a discrete random variable, okay, so we have, so if y is a discrete random variable, we have that the expectation of, so y is discrete, and by definition, that this is the zero times the probability, the indicator, because indicator function is also discrete. So now we are in the case that both of the random variables are discrete. So we can use proposition 7.5.1 point D, part D, okay? All right, so this is 1 given plus 1 times probability, the indicator. Oh. 1A. Okay? So this is the way we compute the conditional expectation. Okay? Okay, by definition we have this. Okay, or if you like, you can see here. So this is the x and the x, and probability that 1a equal to x given okay, so we can use the conditional PMF. Okay, this is a conditional PMF of discrete random variable 1a given that discrete random variable y equal to d to y. Okay, and as we know that x takes only two possible values, either 0 or x. So this is 0 times okay, and so this is equal to p, and what is this? This is actually the probability that indicator is 1 and discrete number is y here. Okay, and this event is actually probability of A given that. Okay, so it is the conditional probability of event A given that the event given the event y equals to d to y. And we know that it can be is this one intersect but if 0, this is the probability of A. Right. So we know how to compute this conditional probability. Okay, and so this is a function of beta y. All right, this is a function of beta y. So that probability of A, which is expectation of 1A, and which is okay, and so this is summation of y. Okay, so this is the marginal PMF of y here. Okay, so this is from proposition 7.5.1.d, or you can say it's from proposition 75.8, right? Anyway, okay, and this is okay. So that this is expectation of P of A given Y. Okay, so you can deduce, maybe I use this. Our proposition 7.5.1.d. Right, so for this special case, when y is discrete, actually you can get this formula. Okay, you can directly. Okay, you can get the formula directly. Okay. So you can also, for this special case, the second one, right, so this is also give us a hint why we call this conditional expectation as the conditional probability of event A given the sign information. Okay? So why we call it conditional probability? Because this is a conditional expectation of this random variable, right? This indicator. But we also call it this one. Okay. And that maybe you can see that this is, for discrete, it's quite easy directly. That because that the conditional expectation of the indicator of an event A, given that y equal to y, for the discrete case, give us the conditional probability of event A, given that y, discrete random variable y equal to y. Okay, from here. Right. So this is justify the name here. A further justification is that we consider the case. Second, when y is conditionally absolutely continuous given the discrete random variable indicator of A, right? So this is, now we consider the first part of proposition 7.5.1. Okay? Now we have here that the expectation of discrete random variable given the continuous random variable y has specific value little y. Okay, so now y is a continuous random variable. Okay. And again, we know that this is actually equal to the, so it is equal to that. Is equal to the summation of x and the x and the PMF P of 1a given y, x given y. Okay? Okay. Okay, so this conditional PMF of the indicator of event A given a continuous random variable y, okay, has been treated in the first part of proposition 7.5.1. Okay, and because there are only two possible values for the indicator, so this is 0.p. Okay, plus 1 times p right here. Okay, and what is that? This is actually, it is the p, so it's p 1a given y, 1, y here. Okay, and so this is actually is equal to and the PMF of 1 sub a 1 divided by if it's positive, and this is the probability of 1a 1, and what is that? This is actually the probability that 1a equal to 1, and so which is P of A if equal to 0. Okay. So by definition, this is this one. And so that this is actually we usually given, okay, and so this is the probability of A given that, okay. So when here, because this is the conditional PMF of the discrete random variable 1 sub a, given that y equal to y. Okay, so this, And this is actually the event A. Okay? Event A here. Okay, so that then the probability of A is expectation of 1A. Is expectation of 1A. And so here is proposition 7.5.1. D-AC. Okay, because we are conditioning on an absolute continuous random variable y here. Okay, and so this is equal to here. Okay. So this is actually okay. Okay, so again, we just define the name, all right, to rename this conditional expectation as the conditional probability of an event. Okay. So both 1 and 2 justify to rename as okay. This is about a remark. Any questions? Okay. Now, when we consider expectation, now in the early sections of this chapter, we prove the linearity, right? Actually, that would be, I think that is proposition 7.2.8. Okay, so for the unconditional expectation, unconditional, right? Just the expectation. We have linearity. Okay, we have linearity. All right, and so just as okay, so we state the linearity of conditional expectation in here. So proposition 7.5.e is called the linearity of conditional expectation. So let x1, x2 up to xm be random variables with finite expectation. Right? So we have m random variables, and each of them has a finite expectation. And we let y1, y2 up to yn be arbitrary random variables. Okay? And then for any a1, a2 up to an in R, we have so the okay, so we form a linear combination of the x sub i's. Okay, so this is the linear, and because xy, x2, xn, they have finite expectations, so their linear combination is also has a finite expectation. Okay, so this one has finite expectation too, by the linearity of expectation. And so now with the sum information y1 up to yn, then this has become to the same linear combination of the conditional expectation of x sub I given y1, y2 up to yn. Okay, so with probability 1. Okay, because they are random variables. Okay, so that the equality holds. Okay, with probability 1. Okay, so this is called the linearity of conditional expectations. Now we are able to give a proof of this proposition as follows. Right? So the linear combination has a finite expectation. With expectation equal to the same form of linear combination. Okay. By proposition (7.2.a). Right? So in 7.2.a, we have shown that we have linearity. Now, by proposition 7.5.a, which says the existence of the conditional expectation. Now, the conditional expectation Z over of Z x1 up to xn respectively given y1, y2 up to yn exists and are unique up to with probability 1. Okay? Now it is clear that G of y1, y2 define okay, and with oh, I forgot to say. And relate, okay, G be version, be a version of E all right, okay, with a version. Maybe I simplify with a version respectively. Okay, so G is a version of this one, this condition expectation, and G1 is a version of this, and up to G sub M, sorry, is a version of expectation, condition expectation of X sub M given up to Yn. Okay. Now it is clear that h of y1, y2 up to yn, ai and gi, y1, y2, and is a Borel measurable real value function of y1, y2, up to yn in R. And okay, I should do a correction here. Okay, so define a new function, right, which is the linear combination with the same coefficient s sub I of g sub I. Okay, so this is some explorable measurable real value function. And when we take the expectation of h of y1, okay, then this one is the summation ai, gi, y. Okay, so we have that. Is that okay? Because this function is the sum of these functions, so that this is this one. And by linearity of expectation, okay, so this is by proposition 7.2.8, the linearity of expectation. So we have that. Okay, and so this is it. But this is a version, right? This is a version. G sub I is a version of the conditional expectation of x sub I given y1, y2 of yn. Okay, so you can see that this is actually xi okay, and so that this is ai expectation of xi. Is that okay? And again, by linearity of expectation, this is equal to again, so by proposition 7.2.8. Okay, and so that this is exactly expectation of z. Okay, so we have that. We have this, right? So the expectation of this function of y1, y2 of yn is equal to Ez. Now, proposition 7.5.8, the uniqueness of conditional expectation, so that h of y1, y2 up to yn, right, is a version of the conditional expectation of z given y up to yn. Okay? So this is a version. And so by proposition 7.5.8, all right, so H, so that, because G is another version, right, so G of y1, y2, so we have here that G of y1, yn, okay, is equal to H of y1, y2 up to yn with probability 1. It's a probability 1, okay? And so this is equal to AI and GI of y1 with probability 1. Okay? So that the expectation of Z, y1, the conditional expectation of Z, right, is equal to the summation with probability 1. Okay? So we have done. So basically, we use the linearity of unconditional expectation to prove the linearity of conditional expectation. Okay. But we have to use the existence and the uniqueness of conditional expectation stated in proposition 7.5.8. Okay, to see that. Okay. All right. So let's take a break up to 2:40. Okay. All right, so we will present an inequality for condition expectation. All right. Now I will introduce a very special kind of function, a real valued function. By phi of x on R is called convex if by phi of alpha x plus 1 minus alpha y is less than or equal to alpha times by phi x plus 1 minus alpha times by phi y. Okay, for all xy in R and for all alpha in between 0 and 1. Okay, so convex function is quite often to observe. For example, this is a convex function. So this is x by phi. All right, so if you you pick up a point, so this is x. Maybe it's too smooth. Maybe I'll use. Okay. All right. So this is x. This is y. And here is alpha x plus minus alpha y. So for alpha in between 0 and 1, this so-called convex combination, okay, a convex combination is a special kind of linear combination, but the coefficient are non-negative and their sum is equal to 1. Okay, so this is called a convex combination. Okay, and the function value here so this is f of x. This is f of y. Okay, and because it's convex, so the chord, this is the chord connecting these 2 points. So the points here, so this is y, f by phi, oh, not f, just by phi. So this is by phi y, and this is the point x and by phi of x. All right, and the chord will be above the curve of the function. All right, and so that so with the same proportion, okay, so we will have a point all right, so and go to here. All right, so this is alpha of by phi x plus 1 minus alpha by phi y. Okay. Okay, so this point. Okay. So I will see this point would be alpha x plus 1 minus alpha y, and alpha by phi x plus 1 minus alpha by phi y here. But here, this is the point with alpha x 1 minus alpha y plus, and the function value alpha x plus 1 minus alpha y. Okay, here. And because this is above, because this is it's a convex, so that this linear combination is greater than or equal to the function value here. Okay, so you can see here, this is the point, right? And the y coordinate is equal to the same convex combination of the two function values here. So this is the right-hand side. But the point here on the curve, right, of this function is the phi of the convex combination of x and y. Okay, so you can see the inequality. Okay. Okay, and so you can see the convexity from this picture here, right? This is about the convexity of a function. But its algebraic definition is here, is by using this inequality. Okay, so if this is true for all x, y in R and for all alpha in between 0 and 1, then this function by phi is called convex. Okay, it's called convex. Okay, examples of convex function are such as the square function is a convex function, okay, and the exponential function is also a convex function, okay, right? Exponential function is also convex, and the etc., etc. So there are a lot of important functions which are convex functions. Okay, but logarithm is not convex; it's concave. Concave means that if the inequality changes the direction. Okay, so logarithm is a concave function. Okay. And the square root function on the positive ray is also a concave function too. Okay. Anyway, so you can see there are a lot of convex functions, and I would like to make a remark. It can be shown that any convex function, convex real valued function, on R, okay, is continuous. So, and then the real measurable. Okay, so any convex real value function on R is continuous on R, and so it is Borel measurable. Okay, now, so I state Jensen's inequality in proposition 7.5.f. So this is Jensen's inequality for conditional expectation Okay, so let x be a random variable with finite expectation. Now we let phi x be a convex real valued function on R such that by phi of x, because by phi a convex function is Borel measurable, so by phi of x is also a random variable, right? So that by phi of x has a finite expectation. It is possible that when x has a finite expectation, but by phi x has no finite expectation. For example, if by phi is exponential function, then quite often, in many cases, that by phi x has infinite expectation. Okay, they are quite often to have that. So we require that by phi x has a finite expectation. Okay. Then for arbitrary random variables y1, y2 up to yn, we have that the conditional expectation, of x given y1, y2, yn, so it's a random variable. This random variable also has finite expectation, and we take by phi. So we use the convex function as the data processing function. Okay, on this conditional expectation. Right? Then this random variable will be less than or equal to the expectation of by phi x given y1, y2 up to yn with probability 1. Okay. Right? So we have inequalities between two random variables. Okay? Between the random variables. Okay. And so this inequality is good for any convex functions such that by phi x has finite expectation and the original random variable x has the finite expectation too. Okay. Now we will use Jensen's inequality to prove the following important proposition. So now let x be a random variables with second moment. Okay? So if x is a random variable with second moment, then we often have a question that for arbitrary random variables, y1, y2 up to yn, the conditional expectation of x given y1, y2 up to yn, okay, has finite second moment too. Okay, so it also, this is quite natural, right? X is a random variable with finite second moment. Now, what about this one? how about this conditional expectation of x given 1 over 2 of n? Okay, we will have, does it have finite second moment? Okay, this is a quite natural question. And this proposition says that yes, this conditional expectation of x given the sign information here has finite expectation. And this second moment, which is no greater than, is no greater than the second moment of x. Okay, so this conditional expectation, this conditional expectation has finite second moment, and furthermore, its second moment is less than or equal to, right, the second moment of x. Okay, so we have the possibility, right? We are able to reduce the second moment, okay, by taking conditioning. Okay, very interesting result you see here. Okay, so once you give sign informations, then this random variable, this conditional expectation of x given 1 over 2 n has the second moment which is less than or equal to the second moment of the original random variable x. And we will see that this proposition, this result, is due to Jensen's inequality. Right, so we use the convex function we use is the square function. So square function is a convex function. On R. And both x and phi x, which is the x square, has finite expectation. Okay? So we know if a random variable has finite second moment, then it has finite first moment, right? This is a proposition I ask you to prove, right? And I think in section 7.4 in exercise 11, I believe. Okay, so is that right? Yeah, in exercise 11. So so x has finite expectation, and the x square has finite expectation too. All right, so we meet the condition required for the Jensen's inequality, right? So x is finite expectation by phi convex, and by phi of x has finite expectation too. All right, so we have, now we can apply Jensen's inequality. Okay, so now the square here, this is square, so it is the right. So the square of this condition expectation is we apply the phi function on that, and we know this is with probability 1 by Jensen's inequality in proposition 7.5 F here. And this is actually in here. Okay, so that this is the condition expectation we have. All right, so that if we take the expectation then the expectation will be less than or equal to the expectation of this random variable. But this is exactly the expectation of x squared. Okay, and the inequality is actually from where? From this is from because both of them are non-negative, so we can use proposition 7.4.b. Okay, so in proposition 7.4.b, we have proved that if a random variable is less than or equal to another random variable with probability 1, then their expectation has the same inequality. Okay? So they have the same inequality there. So this is the proposition 7.4.b. Okay? Right? So that the second moment of this condition expectation of x given y1 to y2 is less than or equal to the second moment of x. Okay, and so we have that. Okay, so all right, so now let x be a random variable with finite second moment. All right, and so by the previous proposition, so proposition 7.5.g, this condition expectation of x given an arbitrary random variable y is a random variable with finite second moment for any random variable y. Right? So that's the difference x minus this one. The difference, okay, has finite second moment. So we prove that, I think, is that we proved that in section 7.4. So let's see. All right. Proposition. .f. Okay. So we prove that. Actually, I asked you to prove as an exercise. That's an exercise. So this is the proposition 7.4.f there. Okay, so this one has 7, and then, which means that the square of the difference has a finite expectation. Right? So this is square has finite expectation. Now the conditional expectation of the square of the difference given y of the square of the difference given y will be called the conditional variance of x given y, denoted as or so the conditional variance of random variable x given random variable y is defined to be the conditional expectation of the square of the difference given y. Okay. So it's a random variable. Okay. Of course, it's a random variable f. Right? So you have to notice that the procedure to find the conditional variance of random variable x given random variable y is first you should define the conditional expectation of x given y, right? And take the difference, right? X minus this conditional expectation of x given y. Take the difference and then square it. Square it. So this is a new random variable. Okay? And then you take the conditional expectation of this new random variable given y. Okay, so you have several steps to do it. Okay. Right now, we would like to simplify the formula of conditional variance of x given y, just like the variance before, okay, of a random variable. Okay, we want to simplify it. So how do we do that? So since the variance of, by definition, we know is this one, right? So that we can multiply. We can expand the square out. So this is x squared minus 2 times x expectation of and plus and y. Okay, so we have three terms there. So now we can apply the linearity of conditional expectation. Okay, so this becomes to be okay, and this is with probability 1 by proposition or by linearity. Okay, in proposition 7.5.e. Okay, so we have that. So this is with probability 1 the same. Okay, now here, this one, we apply the moving out property because the conditional expectation of x given y is a function of y. Okay, it's a function of y, so you can move it out. So this is expectation of x, y. So once you move it out, you get this one. Okay, and similarly, here is a function of y, so that this is equal to square expectation of 1 even y. Okay, and this is exactly equal to, okay, so this is by the moving out property. In proposition 7.5 to b. Okay, so this is the moving out property we have. And so you see this is the square of the conditional expectation of x given y. And so now we get a very nice property. And don't forget that this is with probability 1. This is also with probability 1 here, okay? With probability 1. So now we have the conditional variance of x given y is equal to the conditional expectation of x squared given y minus the square of the conditional expectation of x given y here. And this identity is with probability 1. Okay? So we have the identity with probability 1. That this is it, what we have. Okay? Any questions? Okay, no question. Then I stop here, and I will see you on Thursday.